Hey everyone, and welcome. Today, we're going to pull back the curtain on the magic that's happening inside, well, pretty much all of your favorite gadgets. We're diving into logic gates, these tiny, invisible decision makers that are, and this is no exaggeration, the brains behind our entire digital world. I mean, have you ever really stopped to think about that? How do these devices actually know what to do? It feels like magic, but it's not. It's logic. Billions and billions of tiny, unbelievably fast decisions happening every single second. And it all starts with something that's actually really, really simple. And here's the answer. The logic gate. The best way to think of it is like a microscopic gatekeeper. It's a tiny little switch that looks at one or more inputs, follows one simple rule, and then produces exactly one output. And it all happens in the language of computers, which is, of course, binary. A 1 means true or on. We call that a high signal. And a 0 means false or off. That's a low signal. So how do these super simple gates come together to create what feels like complex thoughts? Well, it all starts with the absolute basics. We're going to look at the 3 gates that form the foundation for literally everything else. So meet the core trio, and, or, and not. You can think of these as the primary colors of digital logic. Seriously, from just these 3, you can build every other logical operation you can possibly imagine. First up, we've got the AND gate. Now this one's the strict one. It will only, and I mean only, output a 1 if input A and input B are both 1. It's kind of like a safe that needs 2 keys to open. You need the first key and the second key. If you have anything less than both, that safe is staying locked. And here's what that looks like in what's called a truth table, which just shows every possible outcome. You can see the pattern right away. If there's any 0 in the inputs, the output is 0. 0 and 0, you get 0. 0 and 1, still 0. It's only when input A and input B are both 1 that, boom, we get a 1 at the output. It's basically logical multiplication. Okay, next we have the OR gate, and this one is way more relaxed. It will output a 1 if input A is a 1, or if input B is a 1, or if they're both 1. Just think about getting into a house. You could use the front door, or you could use the back door. You only need one of them to be open to get inside, right? That's the OR gate. And you can totally see the difference in its truth table. Just look at that. The only way to get a 0 out of an OR gate is if both inputs are 0. As long as there is at least one 1 coming in, you are always going to get a 1 coming out. And finally, we have the simplest one of all, the NOT gate. You'll also hear it called the inverter. It has just one input, and its only job in life is to flip the signal. That's it. If a 1 goes in, a 0 comes out. If a 0 goes in, a 1 comes out. It's the ultimate contrarian of the digital world. Okay, so we've got the basics down. Now let's look at some really clever combinations. These next 2 gates are so special, they're actually called universal gates, because you can build everything else. Yeah, even our first 3, using just these. So first, let's build ourselves a NAND gate. The name pretty much gives it away. It's a not AND. You literally just take a regular AND gate, and then you stick a NOT gate on its output. Simple as that. And the result is a truth table that is the exact opposite of the AND gate. See? It outputs a 1 in every single case, except when both inputs are 1. You could say it's on by default, and it only turns off when that one specific condition is met. And you guessed it, the exact same logic applies to the NOR gate. It's a NOT OR. You just take the output from a standard OR gate, and you invert it with a NOT gate. Now, the real power of these 2 gates is their incredible efficiency. Because you can construct any other logic function using only NAND gates or only NOR gates, chip designers can build insanely complex circuits using just one single type of building block. This makes them the true unsung workhorses of digital electronics. All right, we're on to our final pair. And I like to call these the specialists because they're designed for one very specific but very important job, comparing things. Meet the XOR gate, which stands for exclusive OR, and its partner, the XNOR gate. Their logic is just beautifully simple. XOR is the different gate. It only outputs a 1 when the inputs are different from each other. And XNOR? It's the same gate. It only outputs a 1 when the inputs are exactly the same. And their truth tables show this off perfectly, side by side. Look at the XOR output. A 1 only happens when the inputs are different. 0 and 1. Now look at XNOR. You only get a 1 when the inputs are the same, both zeros or both ones. They're perfect mirror images, designed specifically for checking if two bits are different or if they're equal. So we've met these 7 simple gates. How in the world do they become the powerful technology we use every single day? Well, the magic isn't in the complexity of the gate itself. The magic is in the scale. By combining millions, or these days billions, of these simple decision makers, engineers can build, well, everything. Just think about a basic alarm system. If the door sensor is on and the alarm is armed, then sound the siren. You just described an AND gate. Now, scale that idea up billions of times, and you get the processor in your computer, the encryption protecting your data, and pretty much all the automated systems that run our world. And this really gets at a fundamental principle, not just in computing, but in so many things. The main takeaway here is that our entire digital universe, with all of its mind-boggling complexity, is built by combining these few simple, logical rules over and over and over again. And that kind of leaves us with a final thought, doesn't it? If our entire technological reality can be built from just a handful of true-false questions asked at lightning speed, what other incredibly complex and beautiful systems can be built from the simplest of foundations? Thanks for watching.